Welcome to the uncertainty video just for tables and for log and ln, the special case. If you're familiar with the first part but you don't know how to deal with logs and lns, use the video description and jump to the later part so you can just go and see. Okay, so the first part we'll look at AS uncertainties, a quick, old stuff. Then half the range method, I'll remind you about that, and of course the important special case, logs and lns. They have a special way to calculate identities that you have not learned before in AS. Let's go and see. Okay, so in the intro video, the previous one that we have already posted, you can look at a reminder of some of the common uncertainty identities that you learn in AS. Okay, if you have two quantities added, then you add the uncertainty, absolute uncertainty. Okay, what if there's multiplication or division? This one here. Then you have to deal with percentage or fractional uncertainty, and this was it's called, percentage or fractional uncertainties. Go and review a little bit how to do this. Okay, so this whole thing is a percentage uncertainty, or you can change it to this fraction. So if you want percentage, you just do like that, delta. Percentage uncertainty of A is percentage uncertainty of B. No matter whether it's divide or multiply, you just add their percentage or fraction. Because, this thing. Okay, so each B, C, D contribute uncertainty. If you have power, you also have to deal with percentage or fractional uncertainties. But it depends on what power it is. Power n, then you times n. Okay, so if you want to write it in percentage uncertainty, you can say percentage uncertainty in A is the power times the percentage uncertainty of B. This is how you can calculate. Now, when you come across logs or lns, one method is to use the foolproof method, and the foolproof method is this one. Also seen before in AS, half the range. So if you want to find the uncertainty in the log value, you do maximum number minus minimum number divided by 2, half the range. This one, in case you panic your exam, just use this method. It'll take a while to press calculator, but it will get you to the where you want to go. So we're going to try both methods later when we come to a log question. But let's look at an example to get us practicing how to calculate this thing. Okay, back to the same one that we looked at earlier. ON18 P51 Q2. Here we are calculating voltage and 1 over V. So if you go down a little bit, they will usually tell you what to calculate. Circle it. Include absolute uncertainty in what they want you to find. They'll tell you. So circle, highlight, cannot bring highlighter to exam, right? So you need to know, my table should have space for that. No space, never mind. So if you should only write one value, 0.800 plus minus something. So your plus minus is the uncertainty that you need to calculate. So let's do it in another color, purple. So you need to plus minus some value. But how to calculate uncertainty? This is like an AS question. Let me rephrase for you. Have you seen this question before in AS? V is 1.25 plus minus 0.05 kilovolt. And then they say some calculated value, I don't know what to call it. P is calculated with the equation 1 over V. Find the uncertainty in P. It's basically the same thing that you're going to do here, except that not P We're going to call this calculated value. And you need to find the percentage uncertainty. Absolute uncertainty in the calculated value. How you know absolute? Because same unit You do something plus minus something times 10 to the 3 volt negative 1. Okay, so it's paper 2 question. Look very familiar, right? Okay, so you need to fill in the blank, which is what you're trying to do here in the purple part. Plus minus something something something. So you need to know, this one uncertainty in V, percentage uncertainty in V equals to percentage uncertainty in the calculated value, which is 1 over V. So you can convert, or you can do the fractional uncertainty method. So uncertainty in V over value is uncertainty in 1 over V, which is what you're trying to find, over the over 1 over V, the value of that. This is fractional or percentage method, up to you. You want to use this one also can, this one also can. So usually it's easier to do the fractional method now, because all this thing you do is only 1 mark. See the 2b above my head here? So don't spend too much time writing your full working. If you can just use your calculator and fly with it, Please do that. So, if you want to do this, you will have to do, what is delta V? 0.05 over the measurement equals to the uncertainty we're trying to find over, okay, this is when you have to pick whatever value lah, 0.800. Wow, then you find a number, which should be, I need my calculator a bit. So let's do some calculation, times 0.8. Wow, fraction. Okay, no fraction. 0.032. Okay. So what do we write? Do we write the whole thing? Is there a convention for uncertainty decimal places? Well, kind of, but not strictly. Because if you look at the mark scheme, they barely mention uncertainties, SF or DP. So compared to paper 2 and AS, they really don't care too much lah. The only guideline you need to know though is you need to check, is this precise enough for what you are plotting? So if you look at your graph, you will need to plot uncertainties later. So you need to know one box, how is this? 0.01. One box is 0.01. So uncertainty should be able to give you a precision of 0.01. Can this plot 0.01? 0.01 can. 3 boxes law. This one is 3 boxes in your graph. So really don't care. You can do 0.032 or 0.03. Okay, so this will be 3 boxes when you plot it later. And if you look at the mark scheme, they're not very helpful because they just give you a somewhere here to somewhere here, okay already lah. Okay, so they only give this 0.01 here, only 2 dp, because that's the smallest you need for one box. If you write any more than that, you still have to round it off. So what I will encourage you is, if you are trying to write out decimal places, let's say I chose this 0.8 as my value. This is 3 dp, right? Then your uncertainty can be roughly around 2 to 4 dp lah. We really don't care. Somewhere there, okay already. Okay, can be less, can be equal, can be one more. As long as you can plot it, we are happy with that. So I would probably, if I'm lazy, I would just write this on my paper. 0.03 is fine. But if you feel a bit unsecure, you're like, but it looks like so few dp. Okay lah, then you write this one also can. They really don't care. They're fine with anything. So you can do the same for the rest. This one you can write 0.045 or 0.05 also can, because you have to round off anyway eventually. This will be 0.04. I know I'm just gonna write the short one. So 0.05. 0.04, 0.05, 0.04. It's a weird one. 0.06. Okay. So go and calculate every single one of them. Don't spend too much time. Only 1 mark. Then you have to do your plotting. So you see 0.05 to 0.03, 0.06, they're fine. They're good. They don't care too much. During exam, if you run out of time, you have no time to calculate. Just create some values lah. You find the first one, you find the last one, and just write everything in between. You know what I mean? First one is 0.03. Last one is 0.06. The rest you just write 0.0454545. It's fine. Okay? If you are short of time, you can do that. Now let's look at another example. Okay, so remember this one, no need to show working. If you can calculator, just do it. Now the special case though is the log and ln. How do we calculate uncertainty for log and ln? We haven't learned an identity leh. So what do you do if you are given a value, say for example 1.38, and they ask you, find the uncertainty in log, wow, shortcut LG, log of x. How to find? We don't know an equation for this. So actually method 1 is to use half the range. So I'm going to write here method 1, half range. It's the brute foolproof method lah, but a lot of things to press. So if this one is plus minus 0.02, then if your half range method, you want to find the uncertainty in, let's say, log x. This will mean you are going to do half of the range. So what's the range? Log of the biggest value of x, x maximum, minus log of the minimum value, so x minimum. Divide by 2. No need divide by 2. Why do I always do the divide by 2? Nonsense. Okay, like that can already. Okay, so if you want to write it out, actually, it will look like this. So log of 1.40 minus log of 1.36. There, and you will find your answer. So this is the foolproof method. A lot of calculation pressing. There's ways to shorten it a bit, but never mind. This is one method. The second method is to actually use an identity that we have not seen before. So this one, make sure to write it down somewhere in your notes or sticky pad on your wall. Stick it big on your wall. So the second thing is to use what we call the log uncertainty identity. The general form looks like this. Whoo, here we go. So if you want to find the uncertainty in log of some base A, can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, can be E. I don't know what base it is. Find the log base A of a certain value, X. Like this. Then you want to find it, this is what you can do in your calculator. Do 1 over natural log of A, the base, times what measurement uncertainty over the measurement itself. Wow, what is this, miss? You write down first, then we'll practice. At the end, I will show you a derivation to where this comes from. So if you're interested, you can stay until the end or jump to the end. But there's some maths involved. Okay, anyway, so this is a general equation. Write it down, please. There are two specific cases when you are doing logs. So if your base is 10, then it becomes log 10. So you are doing this. Log 10, right, of x equals to 1 over ln 10 delta x over x. In other words, you can just shorten and say, hiya, LGX equals to 1 over natural log 10 is a constant times delta x over x. Ta-da! Okay, so that is how you can calculate the first one. What if the other case, if your base is a natural number E? Remember we saw the natural number just now? That means it's a natural log. So when you write log E, we are lazy, so we will change the name. Anyway, so this is ln E delta x over x. I just substitute the base only. This is the only thing that will change lah. Okay, one is E, one is 10. So you simplify a bit here, will become delta ln of x, whatever number is. Okay, if you want to find the uncertainty, here's what you need to press in your calculator. 1 over ln E delta x over x. They say, eh, miss, ln E, isn't it? 1? Are you sure? Let's check. So if you look at your calculator, you press ln of E, then it just becomes 1. Why is it 1? Go and ask your friends who take maths. Okay, so ln E is 1, very nice. So we can just we can shorten this even more. So this is gone. It just becomes 1. So all that's left is delta x over x. Okay, so I recommend you to know this general equation up here, but it is also convenient if you know the other forms, like if it's a log base 10, or if it is a log base E, also known as ln. Write down these identities somewhere. For real, do that. Okay? Or you'll be doing this method. Half range, half range, half range. A lot of calculation also. Okay? So let's look at an example of applying this thing, uncertainty identity, in this question. Okay. I didn't write the values. Okay, let me write it now. So this is from the question before. We have already looked at how we got these values calculated. Okay, and the convention, the special case for logs. Now, what are we supposed to find uncertainty for? Yes. Circle or underline. Include the absolute uncertainty for log of t, time. So this is 3 marks. So when there are logs involved, usually they'll give you a little bit more marks lah, okay? Because all these conventions. So we only want log t uncertainty. So I've left some space there so we can write it out. Plus minus. Okay, what method should we use? Let's use both. Why not? So the first method I'm going to write in purple is using method 1. So I am going to do this thing. If I want to find the uncertainty in log of t in the unit of seconds, okay, I don't want to write the seconds, then I will need to do half of log maximum t. You know what, there's too many brackets. Let's use square bracket. So log of maximum t minus log of minimum t. How to know what is maximum, what is minimum? Look at the table. This is the t value, right? What's the biggest it can be? So the maximum it can be is 28. The minimum it can be is 24 minus 4 is 20. So you can do log 28 minus log 20. Press calculator. Know how to press calculator, right? Okay, I show you since this is log. Because some of us have not seen logs before. Maybe, hopefully you have. So you can do half. If you want to do it nicely, you can do a half and bracket. Actually, let's do fractions. Yes. So the half is down there. So you have LG means log base 10. So if your calculator has this, you just press log. Maximum T, 28. Oh, miss, how about 10 to the power of 3? Need to write. Actually, no need, but if you feel very scared, you want to write, write lah. I'll show you why later, no need, because it's a trick of logs. So anyway, 28 is the biggest value. 24 plus 4 times 10 power 3. Okay. Minus log of minimum is what? 24 minus 4, so it's 20 times 10 to the 3. So that's half your range already, lo. So you get 0.073. How many dp to leave? It's very flexy. So let me just write down the value first. 0.073. I would suggest, first step, check your graph. What is the smallest one box? Just now we already said, so one box is 0.02. Your uncertainty can plot 0.02, okay liao lor. So 0.07 is really enough already. But another method or another convention to keep an eye out is, if this fella is 2 dp, then you can do 1 to 3 dp lah. It's really fine. We are fine with that. As long as you're somewhere close to your value, you're fine. So I don't like decimal places, so I would prefer to write just 0.07. Convenience sake, a little bit. Because it's close to this value lor. Okay, so you do the second one, you should get plus minus 0.04. Third one, plus minus, this one got 3 dp already now. Okay lor, so I give you one more lor. So this one can be 0.02, or if you feel like a bit stressed, like, it doesn't really match. Okay, now 0.023. So this is about 3 dp, 3 dp. 2 to 3 is fine. So this one, 2 to 4 dp is okay. Because it's it's close following your value. 0.02 also can lah. Okay lah, you don't want to write this one. Also can. They don't care. You look at the mask scheme. 0.07, 0.08, 0.05. Somewhere there, then they're okay now. Allow more than one SF. Yeah, the one SF rule is from paper 3. So if you have more than one, you write like this, also okay. Now this one, 5.483, you get 0.011. Okay, so I'm going to pause there. If you are doing this half range method, you'll find like, wow, miss, I press calculator until my hand is very tired. Is there a way to shorten this? Yes. Let's see if we can shorten this. One way is to use log identities to kind of simplify this half range method a little bit. So your half range method, you know, log of t minus log of t means the log can combine into a fraction. So log t max over t min. How we can do this magic? No. This one is because of identity of logs. You have to know the nature of how to combine logs. Okay, so this is how you can combine. Then the half here can become a power. So it becomes log, this whole thing, t max over t min, power of half. Power of half is also known as square root, right? So we can actually just write square root inside there. Aiyo, so crowded. Square root. There we go. So that's a slightly easier way to type it. Maybe, I don't know. Up to you. If you find it easier, you can also use this to press in your calculator. It should be faster. Anyway, for this method, let me just continue on. 0.011. This one, very strange. Also 0.011. The last one, 0.0046. Wow, why must write so many one? Here 3 dp. Okay lah, 0.05 also can. I follow my mood. As long as I can plot this, I am good. Okay, so 3 dp, 2 to 4. Oh yeah, that sounds good. Alright, so this is using the half range method. If you use The other method, will you get the same value? Don't know. Let's check and see. Let's use green color. So method number 2 is to use the identity that we just saw over up there just now. So log t, this is log base 10, right? So log base 10, you're going to do 1 over ln 10 times delta x over x. So let me write this out so you can learn how to use it. So this will be 1 over natural log of 10, because 10 is the base, times delta x, delta t over t. Because we are dealing with time now, so t lo. Okay. So let's do a calculation example. For the first one, here we go. So let's do fractions. Since this calculator can do nice fractions, ln 10. Wow, a bit long on miss. Yeah, lo, you slowly press lo. You will get faster and faster one lah eventually. Okay. So delta t here will be the uncertainty in time, which is 4 seconds, or 4 times 10 to the 3 seconds. So you put 4 times 10 to the 3. And then divide by the actual value of time, which is 24. So okay, 24 times 10 to the 3. Notice something interesting. The times 10 to the 3 actually cancel out. So it doesn't matter if you write times 10 to the 3 or not, because here it just cancel out ma. And actually it's the same case for the half range method also. T max over T min. The prefix will cancel out. So the nice thing is, if you don't write times 10 to the 3 in your calculations, you will still get the correct answer. Yay. Okay, let's press this and see what we get. 0.0723. That is kind of similar to our this one. Oh. If we do 0.07, it's the same lah. But if we do 0.072, slight difference. So let's write it out. Also 0.07. If you write out everything, you will get almost the same thing. 0.04, this one is 0.023, 0.011, 0.011, and also 0.046, 0046 or 0.005. So it's the same thing. Both methods will work. Which one are you more comfy with? It's really up to you. Okay, so keep this in mind when you're doing uncertainties. How to deal with them, what are the identities for log, half the range, or you do the identity method on the right, also okay, you'll be fine. Okay, and just make sure your decimal place is roughly close to your value that you write there. Okay, so see lah. This one roughly should have the similar DP to your value. Can be more, can be less, can be the same. Oh, one more or one less. Now, the final part of today, before I let you go and say bye-bye, is, Miss, where does this identity come from? That is what we're going to answer. So if you feel like I'm good using the thing, I don't need to know the math behind it, it's fine to quit the video and go try out some past years right now. But if you're curious to know where this comes from, stay tuned. We are going to look at a derivation, the origin story of this identity. So the first thing you need to know is actually where we get all these uncertainty identities from. Like all these you learn in AS. Did they just come out of thin air? No, there's actually the math fundamental principle behind it, and that is based on derivatives or differentiation, also known as small change. Delta y, delta x, dy dx. Have you seen this before? Dy dx, delta y, delta x. Delta is also known as uncertainty when we apply in a certain scenario. So the first thing we need to start off with is an equation. So for logs and lns, let's start off with an equation. We need an equation to start with. So let's say if I want to convert a log to base e, log 10 to base e lah. Why we want to do that? Because when we are going to deal with differentiation, we know how to differentiate log base e. We don't know how to differentiate log base 10. It's very complicated. So if you have something like log to some base x, if you want to convert the log base, there's an equation for that, and it looks like this. The new log base e divide by log e of the old base. This is just a formula. You don't need to know where it comes from, okay? One of the formulas. So this is how you can convert something to a different base, and we're going to use this equation throughout the whole thing. So once you have an equation, you can differentiate both sides. Wow, miss can differentiate log. Can. If you haven't learned it, that's okay. So differentiate both sides. If you're curious to know more, ask your friends who take maths. So differentiate both sides with respect to x. In other words, I'm going to say, hey, you have this log equation. I'm just going to copy and paste because I'm lazy to write. But now we want to differentiate. Okay, so we differentiate with respect to what? D by dx. Left side. Right side also must differentiate, right? So leave some space also lah. So this right side also differentiate with respect to x. How to differentiate? The left side, we don't know how to differentiate. So we just leave it as that for now lah. Okay, so this is just d by dx log a. We don't know how to differentiate. Right side, we can take out a constant. So this thing down here, log e to a is a constant. There's no x ma. Okay, so we take it out log e to the a. Then we differentiate all the things that have x inside it. So this will be log e to the x. Log e is also known as ln, right? So we rewrite shortcut a bit. Ln. Okay, so reminder, log e x, we often shortcut and just say ln x. Now, ln x is something that we know how to differentiate. Okay, so if you have taken maths, you will learn that, we differentiate log x, we get what? So this will be log e. Log e is ln, right, miss? Correct. So this one is ln a. Then you differentiate ln x, you will get 1 over x. It just becomes like that. Okay. If you want to know why, you go and ask more friends. Got more derivation if you ask why. So we are stuck here. We have done our differentiation. We have this equation. Does it look very familiar to you? The last step is to actually recognize that differentiation dy dx, d log dx is related to small change, delta. And small change is related to uncertainty. So you can say for small changes in x, means a small variation, a small uncertainty, you can say that d by dx is roughly the same as delta by delta x. Okay, so if it's delta y delta x, that is dy dx. If it's delta log delta x, that is d log dx. So we just write like that. Okay, so from here, we will have something like this. Delta, where am I? Oh yes, delta log ax over delta x equals to 1 over ln a, 1 over x. The reason why we can do this is actually, this one, we can also write it as d. It's a bit crowded, that's why we don't do that. D log ax over dx. Looks very weird, right? But we can do that lah, okay? So this is a by the way. Anyway, we are almost there. So to say, we call delta uncertainties because it's a small change, a variation from the value. So this one, we move the delta x to the other side. You have delta x over x. Ta-da! Does this look familiar? This is the identity that we used just now. Okay, so this is where it came from. The origin story of uncertainty equations actually is based in differentiation. Small change, delta, the d's. And here, from there, we connect to up here already. If it's log base a, log base 10, it becomes this. Log base e, it becomes like this. Okay, beautiful, isn't it? Differentiation and calculus. So that is all for this uncertainty video. How to deal with uncertainties, especially the special cases where you have logs and lns, which is natural log. We didn't do it here, but go find out some past years, try them out, check your answers. We'll be posting a few examples, working through some of these, but that's all for the logs and lns. I will see you in the next video.